Okay, so in terms of why there is nitrate floating around in each of these containers, so you have to think that even though we have a target ion in each of the half cells, right? So in this case, we have zinc positive 2 ions. Here we have copper 2 ions. Zinc ions and copper ions don't really ever show up by themselves, right? So typically there is an ionic compound that there has to be an anion to match up with that cation. Okay, so when you're doing this, typically you want to use an ion that goes with that target that is not interfering. So meaning all of the other ions that are going to be in this cell have to be spectators. Okay, so in general, spectators are group number 1. Okay, so all group number 1 ions. And for anions, that's where we're dealing with positive ions. You'll see that again in a second. And nitrate is the go-to for a spectator that is negatively charged. And the reason for that is because if you recall this from the solubility table, nitrate does not precipitate with anything. So meaning it will be non-reactive with any ion that it happens to come in contact with. Right? You don't want to choose an ion that will interact with something else and then you have side reactions going on. Okay, so that's why you see nitrate kind of in both sides. Now, let's talk about this centerpiece. So this centerpiece is called a salt bridge. Okay, so the reason why it's called a bridge is because it's kind of linking the two half cells together. And the reason why it's called a salt bridge is because inside this tube, and actually this is called a U-tube, the original U-tube. So inside this U-tube, it's filled with a salt solution. So remember, salt just refers to an ionic compound. So you have a solution here that contains ions. Again, you don't want to choose ions that are going to have side reactions that will take away from your two half cells. So notice in here we have sodium and nitrate. Sodium nitrate is inside of this U-tube. It's because sodium is non-interacting and so is nitrate. So this could have been really anything from group 1. So potassium nitrate, the lithium nitrate, that didn't matter. You want to have a spectator ion in that tube. So let's talk about the reason why we need to have this here. So let's talk about the purpose as to why we have this salt bridge. So if you notice, we have some more arrows happening on the inside of our half cells. So let's first talk about the reason why things move to one side or the other. So first of all, you'll notice down here the movement of cations, or positively charged ions, are actually always moving towards the cathode. So I know this is saying, oh, it's moving to the right. If the cathode was on the left, it would be moving to the left. So it's not so much the direction, but what it is moving towards that's important. So positive ions, the reason why they're making their way over to this cathode is because you have to consider where the electrons are coming in. Because these electrons have a negative charge and the electrons are coming over to this electrode, there is an attraction for positive ions to be near this area. So you have here electrons always moving in. Whereas on the opposite side, we have negative ions that are moving to the left or moving towards the anode. An O. And the reason for that is because this is where there is always a lack of electrons. Or, if you want to think of it this way, the electrons are coming into this side. The electrons will repel the negative ions to push away from where the electrons are. So remember, opposites attract and like charges repel. So you'll notice here that the negative nitrate has an arrow pointing away from this cathode, right? So it's repelled. So what happens here is the zinc positive 2, you'll notice there's an arrow going up to move over towards this cathode, right? So the positive ions make their way over. Also, you'll see that they're continuing that trend here. So all of the positive ions that are in this galvanic cell are making their way over to the cathode, and the negative ions are being repelled and making their way over to the anode. Now, the reason behind the salt bridge is you have to have essentially a pathway for these electrons to move. So it's actually not so much about having the nitrate leave here or the zinc leave here. This is part of it actually. But what we want to do is we want to avoid saturation from happening. So for example, let's say there was no salt bridge here and we had this half cell to get in with no link. What would happen is you would have zinc ions produced, and it would reach a point eventually where this solution would become saturated with the maximum amount of zinc ions that it could possibly hold. Okay. Once that happens, zinc ions would actually no longer be produced because there would be nowhere in that solution for it to technically go. So what we want to have happen is we want these zinc ions to continuously be led out of this half cell so that this solution will always have room for the zinc ions to come into solution, right? The saturation point will not be reached. Now, on this side, actually the limiting factor of this galvanic cell will be when these ions of copper 2 run out. So notice this solid piece of zinc is becoming zinc ions. So as long as if we avoid saturation, this reaction will continue. Over here, we have ions that are becoming solid. So once these ions are actually depleted, that's when we're no longer going to have this half reaction occurring and the cell will essentially be dead. So meaning the electrons will no longer be flowing. On this side, you're probably wondering, well, what happens if the zinc runs out? The same thing happens, but the problem is this is very rare that it will run out because there are many, many more atoms of zinc in compared to how many copper 2 ions were added to this solution. So remember that this has a saturation point as well. There's only so many copper 2 ions that could possibly be there. All right, so we're going to go over a lot of this terminology and the different things we just finished saying again as we move forward in the slides. Okay, so we've already discussed the two half reactions that are happening in this galvanic cell, but we haven't mentioned what the agents are. So of course, we looked at this already. So because zinc is being oxidized, it is the reducing agent. Remember, the agent is always the opposite half reaction. Copper ions are being reduced, so copper ions are the oxidizing agents. So, as I mentioned, a nice way to kind of remember which electrode is which. The losing electrons is oxidations always occurs at the anode, or LIOA. And gaining electrons is reduction at the cathode, or GERC, however you want to remember that. Okay, so this is essentially going over the same thing again. So here's our oxidation half cell. We are losing electrons. So notice the flow of electrons. And actually a nice way to remember the flow is it's always from the anode to the cathode. So think of like alphabetical order, right? And notice the voltmeter. We haven't talked about this yet, but in order to determine the voltage that is produced from your electrochemical cell, it's actually a short calculation that has to be done to do that. So we're not there yet, but in this lesson towards the end, we'll talk about how you can actually determine what the potential difference would be or the voltage of our cell. Okay, so we've already mentioned this, but so the solid metal strips that are in our half cells are called electrodes. Okay, so but when you are labeling these, you never call them, oh, this is an electrode, this is an electrode. you have to be specific. Is it an anode or is it a cathode? So your anode will typically decrease in mass. Always look at the reaction to confirm what is happening. And the cathode will typically increase in mass. Again, you look at the half cell reaction in order to determine that. So the electrons will leave from the anode where they are lost, and they travel through our wire to the cathode where they are then gained. So the flow of electrons is always from the anode to the cathode. So think of from A to C. Okay, so we mentioned our salt bridge. So a salt bridge is there in order to balance the flow of ions. So remember, we don't want any one side to be unbalanced. So what we mean by balancing is meaning we don't want to cause saturation on one cell or the other cell. We want the ions to be able to flow, so we avoid saturation. So what we have for our salt bridge is you have a U-shaped tube that is essentially filled with a salt solution that contains spectator ions. We've already looked at that. So cations always move towards the cathode. Anions always move towards the anode. And actually, it's kind of easy to remember because they start with the same letter. So cations go to the cathode, anions to the anode. So please do not remember right side, left side, because this can be drawn in the opposite way, right? Your reduction half cell could have been on the left and oxidation on the right. It's more important to recognize which half cell would they be moving towards. Okay, so we've already mentioned, so a salt bridge contains a strong electrolyte, in other words, an ionic compound that contains only spectator ions, so it will not interfere, right? So meaning spectator. So usually we use sodium nitrate, but there are many ionic compounds that you could use here. The point is you just don't want to have any side reactions occurring. The only reactions we want to have are between our half cells, right? So we want oxidation and we want reduction. Okay, so a couple of other methods of doing this ion movement. It's instead of having a U-tube, there are different kinds of like apparatuses that you can have. So this one is actually, if you notice, this looks like it's two beakers that are actually fused together with this center tube here. So this essentially allows for ion movement, but it still keeps the electrodes separated. So porous discs or cups, which you'll see over here, can be used quite frequently. So think of porous, if you've ever had a flower in a clay pot, I don't know why I draw everything I'm talking about, but if you've ever had a flower in a clay pot, clay is an example of a material that is porous. So what that means is it does not allow large materials to transfer through them, right? So if you have soil in the pot, the soil is not going to come through. But if the particles are small enough, they can make their way through that material. So for example, if you've ever used a clay pot and you add water to it, you'll notice that the pot itself starts to look like it's damp. It's because some of the water is seeping through in that porous clay. So this is the same thing here. The solutions are able to mix here. So ions can travel from one way or another, but you still have a separation of the two half cells. The same thing can happen here in one beaker, but what this is a porous cup. So what it is it's literally like a cup, almost like a test tube shape, but made of the same porous material, so like a clay type material. So what happens is liquid can transfer in and out, and ions as well, can transfer in and out from this cup, but you can have one electrode on the inside and one electron on the outside. So you can have a transfer of ions, but you still have the half cells being completely separated.